So before I get into physics material, here's the stuff going on this week. Lab exam 2 is this week in lab. And lecture quiz 2 is on Wednesday at the end of class. And remember that for all this stuff, it's cumulative. So as you're getting ready for it, be sure to go back to the beginning. Any questions about either of those? All right. So going back to Newton's laws, we've talked about some collections of bodies. There are sort of two ways that this can happen, two possibilities. The first one is that the bodies are positioned in such a way that their accelerations are the same. Let me say same acceleration. So these are things like you could have bodies connected by a cable, or they could be pushing on each other. Okay. And in that case, your first step is you isolate the whole system. To find the acceleration, and then you go from there and you find the contact forces and stuff like that. The other possibility is that you have collections of bodies that have different accelerations. And to do this, you always have to involve pulleys. So that's kind of a giveaway. So examples of this would be like this, or this. Okay. And so what do I mean when I say the acceleration is different? If you look at these in that first category, whatever the acceleration of one of those two bodies is, whatever its acceleration vector is, that's the acceleration vector of the other one too. That's not the case here. Like for the one over here on the left, that mass is going to accelerate in the negative y direction. The rolling thing in this case is going to accelerate in the negative x direction. And if that pulley was on the other side, if the ledge was on the other side, the hanging mass would be accelerating in the negative y direction, and the rolling thing would be accelerating in the positive x direction. Okay, so these have to be treated differently. Okay. And the first step is just being clear about which one of these two things you're talking about. The approach, so what we're talking about now is the collections of bodies with different accelerations. And this always involves pulleys in some way. And the approach, I'm going to first sort of lay out an approach, and then we'll do a few examples. So first, choose one of the bodies. And draw a free body diagram and go through Newton's second law. With the acceleration vector using the variable a. Then after you've done that, isolate the other body. And again, you're going to use Newton's second law. Bless you. But the key thing here is in representing the acceleration vector. So for the acceleration vector, imagine moving the first body one inch in the positive direction. And you're going to use this to figure out how the directions of the accelerations relate to each other. If you move the first body an inch, you have to think, what does the other body do? So you're going to use this to figure out an expression for the acceleration of the second body. It's also going to be using that variable a. And then once you've done this, you're going to solve the system of equations that you have. By substitution or whatever method you want to use for that. Substitution always works. Okay, so let's think about it with these two examples that I have drawn here. So the first step is you just pick a body, and it doesn't matter which one you pick. I guess I usually pick the one that's the farthest to the left is the first one I do. So let's say this is going to be the first body, okay? This body moves up and down, right? So when we represent the acceleration of this, the a is going to be in the y component of the vector, right? So that acceleration is going to say 0a. Are you with me on that? So now think if this system moved in such a way that this went an inch in its positive y direction, where would this one go? It would go in the positive x direction, okay? So if we're going to represent this one as 0a, we're going to represent this one as a0, okay? Now, let's think about this one now. So I'll make this my first body. Again, the acceleration is going to be 0a. So if this goes an inch in the positive y direction, where does this one go? Yeah, negative y. So we're going to represent the acceleration here as 0a and the acceleration here as 0, negative a. Okay? And notice that we have not, by doing that, we haven't chosen the way this system is going to work. We've just chosen relationships between how they move. Like for this one, I said the acceleration of this hanging mass is going to be 0a. Okay? Well, in a way, I sort of by default assumed that it was going to accelerate up. We know that's not going to happen. But all the rest of the math will work itself out for you, you know? So we're going to call this 0a. Once we do all the calculations, we're going to find out that a is negative and that this is accelerating down. Since a is negative, this one that we represented as a0 is now going to have a negative x component and a positive y component, and it's also going to accelerate that way. Okay, so all you're trying to do is figure out, okay, moving in the positive y here relates to moving what direction in x for this one. And the same with this one. Maybe this is heavier, and maybe this is heavier, and the true acceleration is going to be in the negative y. Well, we called this 0a. We called this 0, negative a. So what we'd find out once we solve this problem is that that variable a is going to be negative for this. It's going to be negative for this. And so the vectors are going to be 0, something negative, and this is going to be 0, something positive. That math will all work out. Okay, well, I think the way to go is just do a couple example problems and try to point that out as we're doing it. So let's start out with say we have a rolling cart here. Let's say this is 5 kilograms. And it's connected to a hanging mass of 1 kilogram. And we want to calculate the acceleration vector of the 1 kilogram Okay. I'm going to start out by analyzing the 5 kilogram. By the way, all these answers would come out the same no matter what body you isolate first. You just got to do one first. So the 5 kilogram. We have a weight force of 49.05. A normal force, N. A cable force, T. So Newton's second law says 0, negative 49.05 plus 0N plus T0 is equal to the mass times the acceleration. Is this thing able to accelerate along X or along Y? X, so I'm going to write this as A0. Okay. So we have two equations here. The first one says T is equal to 5A. The second one says negative 49.05 plus N is equal to 0. And now I'll go to the 1 kilogram. There's a weight force down of 1 times 9.81. The cable force, that's the same cable, and so this is T. And so Newton's second law says 0T plus 0, negative 9.81 is equal to the mass times the acceleration vector. So now here's the big step in these. Now we have to figure out how these accelerations relate to each other. Okay, well, for our rolling body, we represented our acceleration as a0. Okay, so you can think of that as like we gave it kind of the default direction of positive x. Okay, so what if you move that 5 kilogram cart 1 inch in the positive x direction? Where would the hanging mass go? Yeah, it would go down negative y. And so I'm going to write this as 0, negative a. Do you follow what I'm saying about that 1 inch motion? It tells you like what axis and what the sign is that you have to represent that a for the second body. This gives two equations. Well, the third equation is pretty useless. But the fourth equation says T minus 9.81 is equal to negative a. I guess I'll just go with this one. All right, well, we're trying to find the acceleration vector of the 1 kilogram. So really what we want is just this. This is the acceleration of the 1 kilogram, which means all we need to solve for is a. Okay, so if you can find any of these equations that'll let you solve for a, that's all you need to do. So I'm going to use equations 2 and 4. They say, no, not 2 and 4, 1 and 4. Okay, so equation 1 says T is equal to 5a. Equation 4 says T minus 9.81 is equal to negative a. I'll substitute equation 1 into equation 4. And so you get 5a minus 9.81 is equal to negative a. So 6a is equal to 9.81. And so a is 1.64 meters per second squared. Plug that back into the circled vector, and you get that the acceleration of the 1 kilogram mass is 0. And notice that negative there. We have to apply that negative, so 0, negative 1.64. Or in other words, it's in the negative y direction at 1.64. Any questions about that? Okay, so this time let's say that there's a pulley attached to the ceiling. Let's say that This mass is, yeah, sure, let's make this one 3 kilograms. Let's make this one 4 kilograms. And we want to find the acceleration vector of the 4 kilogram mass. I'm going to start by isolating the 4 kilogram. There's a weight down of 39.24. There's a cable force up of T. Newton's second law says 0T plus 0, negative 39.24. Is equal to 4 times the acceleration vector. Does this 4 kilogram mass move along X or along Y? Y, so I'm going to just write this as 0A. Notice that if you thought about it for a second, you'd realize that it's going to move in the negative Y direction, accelerate in the negative Y direction, but that just doesn't matter. That sign will work itself out. We just need to get straight which axis it's moving along. Well, there's only one useful equation here. T minus 39.24 is equal to 4A. And this question asks for the acceleration of the 4 kilograms, so this is what we're looking for. Okay, so now a free body diagram of the 3 kilogram. The weight is 29.43. It's the same cable, so this is T. Newton's second law says 0T plus 0, negative 29.43. Is equal to 3 times the acceleration vector of this second body. Okay, well, our default was to say that for the 4 kilogram, it's accelerating in the positive Y. Okay, so if you move the 4 kilogram 1 inch in the positive Y, where does the 3 kilogram go? An inch in the negative Y. And so this is 0, negative A. Again, that's backwards of what it's going to do once we calculate it, but we're just going to, that'll show up as A being negative, and it'll work out just fine. So our second equation says T minus 29.43 is equal to negative 3A. And so those two boxed equations are our system of equations. So equations 1 and 2, I'm going to rewrite equation 1 to say that T is equal to 4A plus 39.24. And then our second equation says T minus 29.43 is equal to negative 3A. I'll substitute the first one into the second one, so we get 4a plus 39.24 minus 29.43 is equal to negative 3a. And so you get 7a is equal to negative 9.81. And so a is equal to negative 1.40. Plug negative 1.40 into this circled vector, and you get that the acceleration of the 4 kilogram is 0, negative 1.40 meters per second squared. What if, a question?
So it doesn't matter which equation you sub into which as long as you're plugging the answer.
That's right. I remember being sort of confused about how systems of equations worked when I was first taking these math classes. And I think really the easiest way to make sense out of it is just this. Like, every equation that you enforce is telling you something that's true, you know? And so if you, as long as you keep coming up with stuff that's true, then, you know, they all give you facts that are important, and you can substitute any one of them into any other one. You can go back. Now, like, what if you're trying to find that value t? You know, what equations can you use to solve for t? Well, you can use any equations that you've written as long as they're all right, you know? So just look for the easiest one to solve for t. I mean, I guess I'd go for this reordered one that already has t separated by itself and plug a in as negative 1.4. Let me calculate what that is. So 4 times negative 1.40 plus 39.24, and you get the tension as 33.64 newtons. Yes?
I may have missed this, but how do you dictate what acceleration vector or what acceleration of the y you add the negative to out of the two different equations?
Oh, well, it just depends on which one the problem is asking for. This specifically asks for the acceleration vector of the 4 kilogram mass. So I'm going to use the acceleration vector from my Newton's second law of the 4 kilogram mass.
Okay, so whatever acceleration vector for this specific body mass you're looking for is the one that you leave positive, and then you make the other one negative.
Whichever one, no, actually, so the first thing you do is just at random pick one of these two bodies to be the first one you analyze. And that one you're going to write as either the acceleration is a0 or 0a, depending on which way it's moving. Okay. Then on the second one, you have to think, okay, if this one moves an inch in that positive y direction, where does the second one move?
Oh, so you're causing the fact that you
exactly.
technically do the inverse and have it be right as well.
Yep. If I would have chosen the 3 as my first body, and then I would have said its acceleration was 0a, I would have said the acceleration of the 4 was 0, negative a. We'd go through all the calculations and we'd get the a value positive 1.40, and the two vectors would end up saying the exact same thing.
Oh, okay. Cool. Thank you.
Okay, I want to show you sort of a funky one. I'm going to do 2 more examples here. So this one is called a block and tackle. So let's say this is 3 kilograms, and there's sort of a more complicated system of pulleys connecting this 3 to this 2. Okay. So the cool thing about this is if you just strung a 2 and a 3 kilogram mass like this over a single pulley, the 3 is going to accelerate down and the 2 is going to accelerate up, right? But with this special configuration of pulleys, what we're going to actually see, this is surprising and it's really cool how it works, is that this 2 kilogram mass is actually going to make that accelerate up, okay? So with this configuration of pulleys and masses, you can use a smaller weight to support a bigger force, okay? This is used in shipyards and railroad yards and stuff for moving big masses around. And so I wanted to show you this block and tackle idea, but really the way it's relevant to what we're talking about now is things are going to get more complicated in this one when we think about the relationships between the accelerations, okay? All right, so notice if this wasn't such an unusual setup, the 2 kilogram would accelerate up and the 3 kilogram would accelerate down. That seems pretty obvious, right? With this elaborate setup, the 3 kilogram is going to go up and the 2 kilogram is going to go down. Okay, so I'm going to start with a free body diagram of the 3 kilogram. And what I'm going to isolate is all of this hanging stuff. Okay? So I'll include the cable that goes under the pulley. And the mass. Okay, are you with me on that? The weight force is 3 times 9.81, 29.43. And now the rules for pulling are parallel to the cable, away from the body, so that way and that way. And since it's the same cable in both cases, they're both T. And then Newton's second law says 0T plus 0T plus 0, negative 29.43 is equal to the mass times the acceleration vector. This is the first body, so all we need to decide is it moving along X or Y? Y, so I'll call this 0A. I guess I haven't chosen what to, let's calculate the acceleration of the 3 kilogram. All right, so I got this first equation that says 2t minus 29.43 is equal to 3a. And now I'll go to the 2 kilogram. There's a weight down of 19.62 and a cable pulling force up, and it's the same cable as before, so this is still T. And Newton's second law says 0T plus 0 negative 19.62 is equal to 2 times the acceleration vector. Okay, now this is where this gets a little tricky. With this setup, if the 3 kilogram goes up an inch, where does this one go? It does go down, that's right, but it doesn't go down an inch. Think if this goes up an inch, it means there has to be an inch taken away from this side and an inch taken away from this side, or the whole thing would be crooked, right? So you have an inch here and an inch here that both get added to this. And so if this goes up an inch, this goes down 2 inches. Okay? And so in this case, I have to write this acceleration vector as 0, 2a. So our second equation is t minus 19.62 is equal to 4a. Now we'll solve those two together. So one says 2t minus 29.43 is equal to 3a. The second one says t minus 19.62 is equal to 4a. I'm going to substitute the second one into the first one. So the second one says t is equal to 4a plus 19.62. If I substitute this in, I get t is equal to, well, so I'm substituting the bottom into the top one. So 2 times what the second equation says t is, which is 4a plus 19.62. Minus 29.43 is equal to 3a. And so we have 8a plus 39.24 minus 29.43 is equal to 3a. And so 5a is equal to, this is negative 9.81. What went wrong here?
Would it be negative 2a?
Oh, yes. Thank you. Exactly. Negative 2a. So this is negative 4a. Negative 4a. So this is negative. This is negative. And so we get so we get 11A is equal to 9.81. And so A is equal to 0.89 meters per second squared. And so the acceleration vector of the 3 kilogram, that's this one, is 0.89. Any questions about that? So there's two reasons I wanted to show you this one. The first is you have this seemingly surprising, impossible case where a lighter thing is lifting a heavier thing. That's what's known as pulley advantage, and it only can happen with this specific configuration of pulleys and stuff. Okay? Basically, you're getting the ceiling to take some of the weight of the other thing. And then the other thing I wanted to show you was this case where the magnitudes of those accelerations aren't the same. So we saw that if this 3 kilogram moved an inch up, the 2 kilogram moved 2 inches down, and that has to go into the equation. Okay. Does anyone like this? Okay, good. 2 people. That's pretty good. I'm going to convince the rest of you how great this is too. I'm not really. I'm just going to keep doing problems like this. You got to convince yourself. Okay, the last example of this type that I want to do is one where we have an incline. So let's say we have a mass on an incline. Let's say this is 1 kilogram. And it's connected over a pulley to another mass of 2 kilograms. And let's say this angle's 20 degrees. And let's say that the coefficient of friction for the 1 kilogram block is 0.2. And let's say at the instant shown, the system is moving this way. I didn't have to do that in the other examples that I've done. I didn't have to tell you which way it's moving because there was no friction in the problem. But with friction, you always have to know the direction things are moving. Yep.
So you said friction is 0.2, but you wrote down 0.1. Which is it?
What did I say?
You said 0.2.
Oh, let's do 0.1 so I don't have to erase it. Okay, so the different thing in this problem is when we do problems of rolling and sliding on inclines, we use a funky coordinate system, right? A rotated coordinate system. When we use stuff that's hanging, we use like a normal coordinate system. So which one of those two do we want to use for this problem? The answer is we're going to use the coordinate system we want for each individual body. And then we can still, at the end, just combine those equations. Okay? Because remember that what we're doing is coming up with two different equations that are both true. We come up with them using different coordinate systems, but once we do that, we have equations that are true, so you can combine them with substitution. Okay, so the coordinate system I'm going to use for the sliding body is this. And the one I'm going to use for the hanging body is this. And let's say we want the acceleration of the 2 kilogram. Okay, so the first body I'm going to isolate is the 1 kilogram. There's a weight of 9.81 newtons. There's a pushing force from the ground of N. There's a friction force opposite the direction of motion that's equal to 0.1 N. And then the only other force on this is the cable force T. We're going to have to use a rotated version of gravity. So this angle, is that going to be 270 minus 20 or 270 plus 20? Yeah, because that blue arc doesn't get all the way to the 270 line, so it has to be 270 minus. So this angle is 270 minus 20. So now Newton's second law says T0 plus negative 0.1 N 0 plus 0 N plus 9.81 times the cosine of 250. 9.81 times the sine of 250. And that's equal to the mass times the acceleration vector. Is this moving along x or along y? X, so I'll just write this as A0. So this comes out to be T minus 0.1 N minus 3.36 is equal to A. And the second equation says N minus 9.22 is equal to 0. And so these are our first two equations. And now we'll go to the 2 kilogram body. We have the weight force down of 19.62. We have a cable force up of T. So Newton's second law says 0T plus 0, negative 19.62 is equal to the mass times the acceleration. Okay, well, if the 1 kilogram mass moves an inch in its positive direction, where does the 2 kilogram mass go? Down, an inch down. So we're going to write this as 0, negative a. And so our third equation says T minus 19.62 is equal to negative 2a. All right, well, this time we have 3 equations. I'll start by writing them all out. So T minus 0.1 n minus 3.36 is equal to a. The second equation says n minus 9.22 is equal to 0. And the third one says T minus 19.62 is equal to negative 2a. Well, n minus 9.22 equals 0 says that n is equal to 9.22. So I'm going to substitute that into one of these equations, the only other one that has n in it, and make this a system of 2 equations for 2 variables. So now we have T minus 0.1 times 9.22 is 0.92 minus 3.36 is equal to a. And the second equation says T, I'll write it as equal to negative 2a plus 19.62. Now substitute equation 2 into equation 1. And you get negative 2a plus 19.62 minus 4.44 4.28. So minus 4.28 is equal to a. And so you get negative 3a is equal to 15.34. And so a is equal to negative 5.11 meters per second squared. Question? Yeah.
Why is it negative 3a? Wouldn't you be able to just add the 2 a's to a single a?
Yeah, it just depends what side you're bringing it over to. I mean, that's, so I subtracted a from both sides to to get the 3A over on the left. And then this should be negative, right?
Yeah.
Okay, so this should be positive. I asked for the acceleration vector of the 2 kilogram, and that is this acceleration vector. Come on. And so the acceleration of the 2 kilogram hanging mass is 0, negative 5.11. So is this system speeding up or slowing down? We have that the 2 kilogram is accelerating down. It was originally moving down, and so it's speeding up. Okay. Any questions about any of those example problems? So really the pulleys are what you're looking for. This is the approach you're going to have to use almost certainly if you have pulleys. Yes?
So with the pulley example from the question before this, if we have like a multi-pulley system, we just like count the amount of pulleys and then like the distance, calculate that? 'Cause like you have like loops at like 2 inches of distance traveled.
Yeah.
Would you usually be able to count the pulleys, like how many 12 there are, and just multiply by the distance, or is that not really possible?
Let me think about how it works. So you could have a system that was like, okay, so you could have your pulleys like this, and then this. And all of these three are supporting some mass. Okay, so if that mass 1 lifted 1 inch, that would be an inch to each side of each one of these pulleys. So 1, 2 inches, 3, 4, 5, 6. And so this would go down 6. So I guess if you count up the hanging pulleys, multiply that by 2, that's what you divide by. And the force in this case, it would be like supporting a force that's 1/6 of the real weight of the object. The downside is, by the way, you can never get something for nothing. Basically, you can never get energy without putting energy in. And so the downside of this is if you're trying to lift this mass N1, this pulley system makes it seem like the force is really small, but to raise this a meter, you have to pull the end down 6 meters, you know? So it's less force. It's kind of the same principle as changing gears on a bicycle. It's less force for each time you pedal, but you got to spin the pedals more times to cover the same distance. Okay. Well, the last thing I want to talk about, I think it's the last thing in Newton's laws, is Newton's third law. And in Newton's, famous book, the wording is something like, for every action, there's an equal and opposite reaction. You've probably heard that before. For every action, there's an equal and opposite reaction. And it's not super clear how to turn that into any kind of mathematical thing, but I think this is a nice way to think about it. Anytime objects A and B are in contact, then the force vector on A by B is the negative of the force on B by A. And what that means is they have the same magnitude, but opposite directions. Okay. So me standing on the floor, I'm applying a force down onto the floor that's equal to my weight, That means that the floor is applying a force up that's with a magnitude equal to my weight to my feet. Okay, that's how Newton's third law works. And I want to talk about that a little bit because in a lot of cases, that's very counterintuitive. I've brought up two common misconceptions before. This is the third one. Okay, so first, before I do this, can anyone remember either of the other two common misconceptions I mentioned?
One was about things moving at the same speed as in free fall.
Oh, that's right. Yep. So that's saying that gravity doesn't make heavier things fall faster. Everything accelerates the same, except that air resistance can have different effects on things. And then the second one was related to the bullet being dropped and shot. It said that that horizontal motion doesn't have any effect on how things fall due to gravity. Now the third one is, okay, common misconception number 3. People often think that in a collision, there's a winner and a loser. And the winner of this collision, you can imagine it being a truck and a little car or a baseball and a bat or anything like that. Then what you picture, most people picture, is that the winner applies a larger force to the loser than vice versa. it makes sense, you know, I mean, it feels right. So the winner applies a bigger force to the loser than vice versa. The reality is, in fact, those two forces must have the same magnitude only the direction is opposite. Okay, so like think about a case where this feels like it doesn't make much sense. Okay, so imagine like a professional baseball player hitting a home run ball, you know, and imagine the collision between the ball and the bat. There's no doubt that the bat is the winner of that collision and the ball is the loser of that collision. You never see the bat fly over the fence and the ball stay where it is, you know what I mean? The ball flies 500 feet or whatever. The bat doesn't look like its motion was affected very much by the ball. And so what I'm saying here, and this is a really important principle, Newton's third law, says that the magnitude of the force the bat applies to the ball is exactly the same as the magnitude of the force the ball applies to the bat. Okay? So how can that like make sense with what we know happens in that, you know, the outcome of that collision? And really, like in most cases, it comes down largely to just mass. If you apply 100 newtons of force to an airplane, it doesn't affect it at all. If you apply 100 newtons of force to a bug, it has a big effect on the bug, okay? And so when the bat and the ball collide, say there's, I don't know what it is, it's a very large force for a very short amount of time, let's say 10,000 newtons, okay? There really is a 10,000 Newton force pushing the ball that way and a 10,000 Newton force pushing the bat that way. The ball, though, is really light. And if you apply a 10,000 Newton force to a ball, you get a huge acceleration, okay? The bat is heavier than the ball, plus it's being held by a 200-pound person, plus that 200-pound person has spiked shoes gripped into the dirt of the earth, you know? And so speaking of the masses, the person just has this huge advantage. And so 10,000 newtons makes the ball fly far away, and it makes the bat not do too much, okay? And so we're gonna do a lab exercise where all you kind of think about is interactions like this. But I want you to keep this in mind as one of those key things. There are 4 of them total in this class. And one of them is this one, that when two things are in contact, no matter how much it looks like one is being treated differently than the other one by this collision, the magnitude of those forces is exactly the same in every case, under every circumstance, and the directions are opposite. Anybody have any questions about that? We've seen that a little bit, by the way, in the way we treat like pushing forces, the way we treat pulling forces. You know, if two things are pushing on each other, when you do their free body diagrams, you say this one has a pushing force of R, this one also has a pushing force of R. The reason that's true is Newton's third law, you know. So we already use it mathematically, but it still takes a little practice to wrap your head around it. Okay, that's all.